All right, I figured I would do a couple more examples of some Lewis structures. So we're going to start with NH3. This one is on the bottom of page 17, and here we go. All right, so the first thing we do is we figure out what the central atom is. Hydrogen is never the central atom. Therefore, our central atom, our thing we're going to place in the middle, is going to be our nitrogen. Hydrogen will never be the central atom. All right, so I'm going to place my nitrogen in the middle, and I'm not going to know if it's right till the end, but I'm going to place one hydrogen there, the second hydrogen there, and the third one, I don't know, right there, okay? So I've got a central atom. Now, I'm going to count up my valence electrons here, right? So I know how many to put in my drawing. And so I go find nitrogen on the periodic table. And so when I pull out the periodic table, I go find nitrogen, right? And so nitrogen is located right here. And all of the elements that are right here all have 5 valence electrons, all of them. And so nitrogen, there's one nitrogen in this formula. Therefore, our valence number for that is 5. Hydrogen, on the other hand, okay, is part of group 1 on the periodic table. It's over here. And it has 1 valence electron, okay? There are 3 hydrogens in NH3, so 1, 1, 1 to reflect the 3 hydrogens. So this is for nitrogen, hydrogen, 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 and H3, okay? All right, so this should be an even number, and indeed it is. When we add this together, we get 8. So what happens here is we then do single bonds for these things, okay? And let me bring this over just a little bit, I think. I tell you, marvels of technology sometimes. Would you stop it? You have a very simple job to do. Please do it. All right. So single bond right here would involve an electron there, an electron there. A single bond here would involve an electron here and an electron here. Single bond, electron, electron. Definitely testing my patience, this thing is today. All right. So what ends up happening now, okay, is we used up 2, 4, 6 of these 8 electrons. So we subtract out those 6, leaving us 2. Now we ask ourselves, we work outside in. So hydrogen, well, most elements want 8 electrons in their outermost level unless they are an exception, right? And so our exceptions are right here. And hydrogen indeed is an exception where hydrogen is happy to only have 2. That makes sense with our Bohr model, doesn't it? Because in that first level, right, that first quantum energy level only has 2 electrons in it, doesn't it? It goes 2, 8, 8, right? 18, 18, 32, 32. And so that makes sense to me. All right, so hydrogen's happy, hydrogen's happy, hydrogen's happy. But this nitrogen in the middle, it's got 2, 4, 6 electrons when it would want 8. It's not an exception written here. It's not, okay? And so what do? Well, we take these last 2 electrons that are right here, and we got to place them somewhere. Well, good, because we needed 2 more in our middle atom anyway, okay? And so we put them in the middle. That takes up our last 2, and we have none left. Now, the next step, though, in our journey is we need to say, okay, then what does this actually look like? What are, so we go over and we look at, now that we've placed our electrons, this chart right here, right? Our VSEPR chart. And so the first thing we need to do is we need to look at our central atom, our nitrogen, and ask how many quote-unquote things there are. And here's how we determine that. Things are structures that are bonded or lone pairs. So we have one thing right here that is bonded. We have a second thing that is bonded. We have a third thing that's bonded. Guys, and it does not matter that we have single bonds, double bonds, triple bonds. It's just how many things are bonded. So one thing that's bonded, 2 things that's bonded, 3. And then we have this thing right here. So that is a total of 4 quote-unquote things. Now, of those 4 things, 3 of them are bonded structures. They're bonded things, 1, 2, and 3. And one of them is this little thing right here called a lone pair. Okay? So we're given 4 things, 3 bonded, 1 that is a pair. And so what we do is we then go over here, we look at our VSEPR chart, and we look for where there are 4 quote-unquote things. So 2, 3, here's the 4s. And we have 3 possibilities for 4s. And we're looking for one where the number of bonds is 3, and the number of lone pairs is 1. Therefore, this would be trigonal pyramidal. So how we should have drawn this is we should have drawn trigonal pyramidal, shouldn't we have? Okay? So trigonal pyramidal. And so let's fix it. So I look at my trigonal pyramidal and I say to myself, okay, I'll put the nitrogen right here in the center. I'm going to put my lone pair coming off of it like so. I'm going to put a hydrogen. I'm going to put a hydrogen. And I'm going to put a hydrogen. This accounts, and you can even, like, if you like putting in your electrons as dots, which I do, you could even do that. And that is the correct answer, not this, but this one is the correct answer. If I asked you the shape, it'd be trigonal pyramidal. If I asked you for the bond angles, these bond angles would be 107.5 degrees apart from one another, and you'd have sp3 hybridization. Okay? All right, let's do the next one together. That's COOH minus. And it says, hint, there are resonance structures, meaning there is more than one correct way of doing this. So COOH, and we can't forget that it's also an ion because it's charged. So we have COOH minus. Okay? So first of all, we got to figure out which thing is the central atom, right? So we go find our electronegativity chart, and we're looking for the one that has the lowest value on this chart. And what it's going to be is it's going to be carbon. Guys, I will tell you that 90% of the time, maybe even more than that, more like 99% of the time, if carbon's involved in something, it's probably the central atom. Okay? And so carbon's the central atom here. And so I'm just going to place carbon in the middle. And then I'm going to place 2 oxygens and a hydrogen around it. I don't know. Oxygen, oxygen, hydrogen. Why? I don't know. I'm just doing it. I'm just putting them somewhere with carbon in the middle. We'll fix it later when we get to the VSEPR thing, right? Where it's actually located. All right? All right, so now we need to count up our electrons. I'm going to bring this a little closer. So carbon, we go find carbon on the periodic table. And on the periodic table, carbon is located right here. And all the elements that are right here have 4 valence electrons. Remember, it goes 1 valence, 2, we skip across, 3 valence, 4, 5, 6, 7, and 8. And so we have 4 for carbon. When we go on the periodic table and look at oxygen, okay, oxygen is a chalcogen, it's right here. All of the chalcogens have 6. Well, there's 2 oxygens in our formula, so 6 and another 6, oxygen and oxygen. And hydrogen has 1. We established that on the last problem, right? All right, so this little thing right here, though. So because this thing has a -1, right, and it's redundant, you don't have to put the 1, right? Just like we didn't put C1, O1, you know, H1, right? We don't put 1s in chemistry because the fact that it exists means there's 1 of it. And so minus, okay, or -1. And so what we have is 4, 6, 6, and 1, but we can't forget about this thing, right? Because this thing means this thing gained an extra negative charge, which is an electron, which is what we're counting right here. So we got to add that in. Now, what should have triggered that for us? If we would have gone to add this up, 4, 6, 6, and 1, we would have gotten 17, wouldn't we have? You're never going to get an odd number on this. How do you do pairs of electrons if you have an odd number? And these are always in pairs. And so that's why this extra 1 just makes sense to me. So, and I hope it does to you now. So 4 plus 6 is 10, 16, 17, and 18 total. All right? Again, that's because of this -1, which is that thing right there. So hydrogen was that one. This is that oxygen. This is that oxygen. That is that carbon, right? That's where those numbers came from. All right, so we single bond them because that's the first step. So there's 2 electrons in that single bond. We single bond here. There's 2 electrons in that one. There's 2 electrons in that one. So we've used up 2, 4, 6, and everybody is bonded. So there is 6 gone from our drawing. 12 electrons to go, okay? And so what ends up happening here now, class, is this. We have to ask ourselves, these outside atoms, are they quote-unquote happy? Well, hydrogen right here with 1, 2 electrons, if we look at our little chart, right, for exceptions, again, hydrogen, more than happy to have 2. So this hydrogen right here, 1, 2 electrons, happy as can be. This oxygen right here has 2, but oxygen wants 8. It's not an exception here. So oxygen wants 8. So therefore, oxygen will do this. It'll say 1, 2, 3, 4, 5, and 6 of these 12, we'll take them. Then this oxygen up here says, well, don't forget about me. I want 8 electrons too. So 1, 2, 3, 4, 5, and 6. We take out those 6, boom. Okay? And so we get this. Now, we start looking to see is everybody happy, and we find out carbon wouldn't be, and here's why. Carbon is not an exception either, and carbon in this instance would only have 2, 4, 6 electrons when it would want 8. And so what do? We have to then put extra electrons here, but there's none left right here, are there? We're to 0. And so what do? We talked about this before. We now make a multiple bond. Well, hydrogen wouldn't make a multiple bond because there's no electrons to swing in from this hydrogen. So it's either this oxygen or this oxygen that are going to do it. Now, so I want to right now fix my VSEPR so that when I go to do the double bonds, I'm drawing it correctly. And so what I'm going to do is I'm going to look at that real quick. Because it won't change my number of things when I take either one of these or one of these and swing it in, right? I'll still have 1, 2, 3 things and no lone pairs. And so on my chart here, right, I go and I find where it says 3 things, 3 of them that are bonded things, and no lone pairs. And it should be trigonal planar. So what I've drawn here is actually correct, right? Now I know on your sheets it looks like a Y, doesn't it? Well, what I've done here is if you turn your head, you'd have a Y right here. Or if you go stand on your head, you'd have a Y right there. So we're good to go on that. Our drawing is okay. All right, so I am going to do one resonance structure first, and I don't know, I'm going to pick the bottom one first. So I'm going to take these electrons, I'm going to swing them in, okay? And so when I do that, here's how my drawing ends up adjusted. Those 2 electrons got swung in to make a double bond right here. We have an oxygen. And then we still had 4 left over. We got to adjust those a little bit because things that are like charged would repel and they'd want to shift a little bit. Okay? So now let's count them. Hydrogen, 1, 2 electrons, it's happy. Oxygen, 1, 2, 3, 4, 5, 6, 7, 8, it's happy. Oxygen, 1, 2, 3, 4, 5, 6, 7, 8, it's happy. Now carbon in the middle, 1, 2, 3, 4, 5, 6, 7, 8, everybody's happy. There is one more small little detail, it is important. Because this is an ion and we have an additional electron added in, this one, we have to tell that to the audience or to the person who's reading it. So we put brackets around it and we put that charge right there, the minus. Now, class, we could have made the double bond with this oxygen, couldn't we? And that's why we need to have resonance structures. And so here's our other possible answer. We could have had carbon with a double bond here, right? And now the 4 electrons would have been left there, right? You would have had one of these pairs swing in, right? I'm going to get rid of that because I don't want that drawn. But that's what would have happened there. When that happened, you would have had 4 electrons left over that would shift. Okay? And so now this one would still be single bonded oxygen, and there would be 6 electrons around the outside of it. And this would still be just hydrogen bonded here. You'd put your brackets around it and your -1 charge. And these are the 2 possible resonance structures for this. And now you've drawn a proper VSEPR. Any questions? I hope you're doing all right.